Hello and welcome. My name is Charles Zona, and I'd like to thank everyone for attending today's McCrone Group webinar. Our presenter today is Craig Schwant of McCrone Associates. Craig is going to tell us about low voltage microanalysis using the scanning electron microscope. But before we get started, I'd like to give you a little bit of Craig's professional background. Craig is the Director of Industrial Services and a Senior Research Scientist with McCrone Associates, and is also a co-instructor for our basic and advanced scanning electron microscopy courses. He specializes in X-ray microanalysis of particles using energy and wavelength dispersive spectrometry methods with the scanning electron microscope and electron microprobe. Craig will field questions from the audience immediately following today's presentation, and this webinar is being recorded and will be available on the McCrone Group website under the Webinars tab. And now I'll hand the program over to Craig.
Thank you for the introduction, Chuck. Hello, and thank you to everyone who's tuned in for taking a few minutes to listen to some thoughts. Conducting low voltage microanalysis with your scanning electron microscope and energy dispersive silicon drift detector. The technological advances afforded by silicon drift detector technology are key to the successful application of low voltage microanalysis. These include both the large area of these detectors, allowing for vastly improved counting efficiency, and their increased sensitivity for low energy X-rays. One of the most important concepts to keep in mind before beginning any microanalysis is to think about the interaction volume produced by the electron beam of your SEM. Remember that the penetration depth of the interaction volume is a function of the beam energy and the average atomic mass of the sample. This stylized interaction volume cartoon reminds us that the majority of characteristic X-rays originate from micrometer depths, especially for conventional microanalysis using beam energies of 15 keV or greater. With interaction volume in mind, the next consideration is the type of sample we wish to analyze, as well as what is our ultimate objective. Do we just want an idea about what something might be, or do we really need to quantify the results? If we want to quantify the results, how accurate do we want to be with these results? The beam energy we select will help achieve correct answers to these questions. Do we want to know about particles? Well, how does one mount those to avoid background interference? Does one have a thick, flat, polished sample, or is one interested in averaging lots of grains, or really quantifying the composition of a metal or a mineral, or perhaps one is interested in minor or trace element compositions associated with biological materials? In 1913, Henry Moseley published his empirical observations that the square roots of characteristic X-ray energy lines were proportional to atomic number. Along with Bohr's model of the atom in 1914, the observations were responsible for ordering of the periodic table based on atomic number. Conventional microanalysis utilizes predominantly K lines with some use of L lines. For low voltage microanalysis, we'll be using more L lines than K lines. Hendrik Kramers described the distribution of X-rays produced when electron beams are hitting a solid target, thus producing a continuum or Bremsstrahlung radiation. As you can see from the red line, ideally the intensity of low energy X-rays should be very high, but in practice we observe this not to be the case due to absorption effects. Absorption is another key factor to be concerned with, especially when conducting low energy microanalysis. As an example of how successful low energy microanalysis can be, I will use a Tourmaline example. Tourmaline is a hexagonal trigonal cyclosilicate mineral containing boron. Borate anions are arranged in threefold symmetry within the aluminosilicate framework. A number of cationic solid substitution possibilities yield a variety of colors to this popular gemstone mineral. The various coupled substitutions are named as end members with specific colors. Conventional microanalysis utilized beam energies of at least 15 keV. Importantly, boron and oxygen were not measured. At beam energies of 10 keV or and higher, boron and oxygen suffer significant absorption effects. Thus, it was either assumed there was little silicon solid substitution, and so analyses were normalized to 6 silicon atoms, and also assumed that boron was stoichiometric, so that oxygen was determined by difference of the analytical total from 100 weight percent. Or alternatively, one could assume the values were stoichiometric to 29 oxygen atoms and boron was determined by difference. Both methods rely on a major assumption and neither element was actually measured. In my specific example, I had tourmaline crystals with chemical growth zonation that I wished to analyze. Here is a transmitted plane polarized light image of one example. There are several factors to be concerned with when conducting low energy microanalysis. The first is whether one should use low vacuum conditions or carbon coat the sample and use high vacuum conditions. We must remember that low energy X-rays are greatly absorbed. The next consideration is to balance the overvoltage with the line selection for the elements of interest. You will likely want to experiment with this a little before actually deciding on the best energy to use. I show the results of using internal standards, but for the absolute best results, one should conduct full measured standards quantitation. This approach, however, often suffers from a lack of matrix match standards, which are, of course, the ideal. Of course, with low voltage microanalysis, there are more peak interferences that occur than conventional microanalysis. Some factors specific to my example include conducting some experiments to establish if there are any crystal orientation effects associated with measuring boron. Also, is a spot or an area analysis better, as these may affect measurement and quantitation of heterogeneous materials. With some experimentation, the first two concerns were established as the most crucial. A reasonable amount of testing was done to determine the best conditions for tourmaline. Peak overlaps were considered to be of less concern, as peak deconvolution algorithms have become very robust. So, deconvolving carbon from the low energy spectrum, such as this, provides a much better result than a situation where we have no idea about how much absorption is taking place and no way to correct for it. In particular, I'm talking about the use of low vacuum conditions. The conditions tested demonstrated significantly diminished boron intensities relative to high vacuum conditions. Thus, in the tourmaline case, the result was much better using carbon coating in high vacuum conditions than low vacuum conditions. Using an Oxford Instruments Aztec system, I set up to use 4,096 channels between 0 and 10 keV and a process time of 5 for excellent energy resolution. I established that a good trade-off for boron intensity as well as calcium kaolin production was an operating condition of 6 keV. I had great oxygen intensity as well as great boron intensity, though it doesn't particularly look that way. Although the carbon intensity from the carbon coating is significant, at least boron is measurable. I used the established stoichiometric formula of tourmaline as published in an Introduction to the Rock-Forming Minerals by Deer, Howey, and Zisman to calculate the composition in terms of weight percent and atomic percent. This is presented along the right side of the slide. The top left results are the quantitative results from Aztec using the Oxford Instruments extended line standard set. The standards were simple oxides, or in the case of boron, a boron nitride. I used some of the electron microprobe standards we have on hand at Macron Associates to conduct a full measured standards-based quantitation, and the results are almost indistinguishable. Importantly, though, I also had to use a boron nitride as a boron standard. If I had used a flat polished tourmaline as a standard, I'm confident that the result would be more accurate in terms of boron concentration. However, a wet chemical analysis method for measuring boron and tourmaline, which does not use a metaborate flux to get the tourmaline into solution, doesn't exist. Also, as boron has a high neutron cross-section, it is not well analyzed by instrumental neutron activation analysis. Other methods require a standard. Thus, the best one can do in this type of situation is to characterize a sample very well and then use it as a standard so that one would at least have an internally consistent set of data. In the case of simple binary compounds such as quartz, the results can be very good. In this slide, we see the results using the internal standards for beam energy conditions of 15 keV and 6 keV. The stoichiometric values are shown in the middle for comparison. In this case, the matrix corrections, although pretty good, are off at lower beam energies. However, if you have matrix match standards with which to conduct full measured standards quantitation, then the results are fantastic. The absorption, fluorescence, and atomic number corrections fall out and leave mostly sample preparation, detector performance relative to energy, and carbon coating differences, as well as window corrections as issues. With more complicated compounds, such as garnet, the results aren't quite as good. The top result was completed using the supplied internal standards. The low voltage analyses utilized full measured binary oxide standards, and the results are not too far afield. However, if we had a matrix matched garnet standard, I expect our low voltage analyses would have been almost as good as the 15 kV results. It does depend on what material you examine, though. In the case of steel alloys, especially stainless steels, the results of low voltage microanalysis are simply bad. For materials that you have worked out the optimal conditions, you can even utilize low voltage conditions to conduct mapping. However, as with all elemental mapping of materials, one needs to establish the appropriate dwell time for the lowest concentration element of interest, or otherwise iteratively accumulate for sufficient peak intensity per pixel. Low voltage microanalysis simply requires a little extra attention to details, such as one would follow for electron probe microanalysis. First, establish what you wish to find out, then use your silicon drift detector to its full capability. I hope you found this presentation useful. Thank you for your time.
Okay, thanks again for attending today's webinar. If you have any questions, please go ahead and start typing them into the questions field, and we'll begin to answer them.
One question was, was there any color change noticed on the stones after analysis? No, not any, so we're not burning these. There's much less opportunity for damaging materials when you use low voltage analyses than if you use high voltage and high probe current analysis.
Okay. Here's a question from Ed. With carbon coating, is there a chance of boron contamination?
Pretty low. Most boron is it's not going to be in a quantity that you'd really pick up in terms of the carbon coating, the amount applied with carbon coating. You might have some fractional percentage of boron in your carbon, but most of the sources, either carbon fiber or carbon rods for carbon evaporation and carbon sputtering, are fairly pure, so there's not likely to be a boron component in those.
Okay. Heather wants to know what detector do you use and from which manufacturer?
In this case, this was an 80 square millimeter X-Max detector from Oxford Instruments, but I could equally have done this with any of the other vendors' instrumentation.
So it's not
vendor specific.
Okay, great. Just in general, Eric wants to kind of know the advantages of low voltage versus high voltage. So summary maybe, Craig,
Yeah,
if you
summary.
can.
So in many cases, again, we'll go back to the beginning where we discussed the penetration depth. So in general, you might want to use low voltage microanalysis to keep the analysis interaction volume very near the surface, so that you don't penetrate deeply into the sample. In my particular case with this example, I was interested in measuring boron and wanted to highlight the sensitivity, the low energy sensitivity of these new silicon drift detectors. But otherwise, it's a combination. Do you need that light element sensitivity? So would you also, you get great response for things with containing nitrogen in, much better than a silly or an older system. So low energy microanalysis and in terms of the elements you measure, and also keeping your interaction volume very near the surface rather than penetrating deeper with higher energy analysis.
Okay. Tatiana wants to know, as it relates to, looks like pigment identification, a complex painting matrix with pigments of high atomic weight, such as lead, mixed with laked pigments.
Yeah, so in many cases there are actually some M lines associated with those that actually are clear enough of other overlaps so that you could experiment with some low energy microanalysis somewhere in the range of 4 to 6 or 7 keV, and it may give you a much better result. Especially if you used a sectioning method to isolate one of the pigments, so you're not, if it were the painting was layered or something, you just want to isolate it to one pigment at a time. I think that the elemental spectra would actually be fine. There's really good response, and in many cases the quantitative results can come out just as well at the low energy, because those M lines and the L lines in this region are very close to the oxygen in terms of energy, so the absorption corrections don't need to be as extreme as if you were using high kV and using a high energy K line with the low oxygen, low energy oxygen line.
Okay. Ed, just going back to your statement that low voltage microanalysis of stainless steels is bad, and you must know, is that due to carbon dioxide absorption on the surface of the stainless steel?
No, it's mostly due to the overlap of the critical elements, constituent elements, the manganese, iron, chromium, nickel. The low energy L lines for those are very overlapped, and it just doesn't make for a very good mix. If you wanted to experiment with using a matrix match stainless steel as a standard, you could perhaps improve it, but it won't work out well if your standard set is with pure metals. Then the matrix corrections that will be applied are going to cause the quantitative result to be in error. So this would be a good case to experiment a little on your own if you have access to stainless steel standard materials, polish them flat, and then use those as, take the measurements and use those as internal standards, and then compare your quantitative results. But it's not due to the carbon dioxide.
Okay, well, I think that actually does it for the questions, Craig. I think we've gone through all of them, and I'd like to thank everybody again for attending today's webinar. And our next webinar is on June 16th, when our presenter will be Jeff McGinn of Micron Microscopes and Accessories. And Jeff's going to be talking about the new JEOL Neoscope. So be sure to tune in next month for another Micron Group webinar. Thanks again for attending.
Thank you.
Bye.